Okay, so good evening everyone and welcome to the 11th session of the course Dynamical System and Control. So today we will be discussing about the optimal control problems. So what optimal control problems look like and how to solve them. So I'll look on few examples as well after discussing the theory part. So you have already seen some notions of optimal control, I mean without even noticing it. Okay, so let me first introduce this example. Okay, so forget about this functional first. So let's forget about this functional. Okay, just consider this control system. So you can clearly see the here x and y are the states. Okay, and this u is the control. Okay, the question is that such x and x, y and u. So the question would be that does there exist x comma y comma u which solves this system. So let me call this system as some C. Solve system C. Okay, so generally what we have seen is if we have been given some differential equation, ordinary differential equation, we have some initial data, right? This is the kind of system what we have studied, that how to solve this ODE. So we have some, even for the non-linear one, so we have seen this kind of things, right? How to solve this ODE, but over here this is the extra condition. Okay, this is something that we want, that at time t equals to 5, the x5 and y5, the value should be 1. Okay, and so if you remove this u, okay, then you know that it cannot be possible, right? Because so this system is basically xy prime equals 0 1 minus 1 and then 0, right? So this is the system. So forget about u. Then the solution of this system would be given by xy, which is et of a. Suppose this is the matrix A. Okay, then exponential times x at 0 and y at 0. Correct? So this is the so this is the solution. Okay, now we know that x at 0, y at 0 is 0. That means the solution, this is equal to 0 comma 0. So you cannot expect that at time 5 it will be 1, right? So they at that point this control comes plays a very vital role, that you want to find a control u so that the trajectory does not remain this. Okay, so it has to be changed so that at time equals to 5, t equals to 5, the solution, so this is at so this is xy at t, right? So you want the value xy at time 5 to be 1 1, right? So that's why this is the purpose of control, right? So we add something, this is called input, so that the trajectory behaves as per your demand. Okay. So we have already discussed this kind of example, correct, related to control problem. So the question is, does there exist some this kind of triplets, that x y u? And the answer is yes, right? So basically the question is, so you forget about this. So you forget about this terminal condition. This is a specific terminal condition. But we know that we can this system, if you write in the matrix form, the system is nothing but xy prime so let's say this is a and this is b. So you know that if you compute the rank of this BAB, this will give the whether the system is controllable or not. So this is some kind of controllability question if you forget about this functional, right? That at 5 can you reach 1? So here we are giving just a particular value of time as well as particular value of the terminal data, that it should be 1 vector, right? So my xt, that terminal data is 1 comma 1. So this is given to you. So if you can prove that this system is controllable, then you can say that okay, this solution exists. Okay, and for that we need to check the rank of this matrix, right? So you can clearly see the b is 1 comma 1 0, and if you multiply ab, then what you get is this will be 0 and this will be minus 1, correct? So the rank is equal to 2. So this would say that okay, the system is controllable. This you can say. So the question, if you forget about the minimizer, this functional, then you know that the solution exists, correct? Now here what we will extra thing what we are putting that okay, we know that the solution exists, okay, but what we want the control u such that the norm of u should be minimum, okay? So this is the goal, that okay, you demand. So the question was this. Now in addition to this question, you have added one more thing, that okay, you know that okay, this solution for this system exists. So you will get the pair x comma u comma x comma y comma u such that this system has a solution, okay? Now this system can have infinite solution, right? The control u need not be unique, right? Control u could be like, we could have many options for choosing the control u, right? So now the question what we are adding is that you have to choose such u, okay, which minimizes which has minimum L2 norm, okay? So this functional should achieve minimum value. So in practical purposes, basically you want to get a optimal control, that is the best control, okay? So this is something like, this is the called control cost sometimes, that how much money you will have to pay to get such controllability, okay? So now you are just asking that okay, we'll get the solution of this system, but I want such solution so that this functional should have minimum value, okay? And you have already seen that such the the control what we have given, like when we were discussing about the controllability, that has minimum L2 norm, that was already discussed, right? So here you are lucky that you know that what the minimal control is, okay? So let me just recall maybe. So over here what you know is this thing, you know, right? So this you know that AB is controllable. Now the question is find U, okay, the control. So find control U such that norm of U L2 0 comma t. So over here t is equal to 5, right? So the final time we have already given. So we want this to be minimum. This is minimum. So if you want, you can denote it by u hat. Okay, so find control u hat or u star, whatever you like, is minimum. So this is the optimal control, that you are asking for a control which has the minimal cost. Okay. So this is the question, and the answer is you already know the answer, right? So the control what we have given earlier, so if you can recall that it was something like so E sorry, first it will be B star, and then you will have E T T naught. So over here, so let me just write, so T naught is given to be 0 and capital T is given to be 5, right? Okay, so first let me write what it is. So T naught minus T A star, and then you have inverse of the controllability Gramian matrix, right? So you have inverse of this, and then you have E of T naught minus T naught minus T A times y1 or x1 over here, right? So here we are dealing with x, so or let me write x5 y5, that is the final value minus the initial value x0 y0, right? So this is the expression of the control that we have seen. So when this rank of this matrix is 2, you know that this W matrix, so what was W? So where W was given by, so it was just the integral from T naught, so over here T naught is 0, so T naught to T, and then you had this E of, so T naught minus T, so minus T A B B star, and then you had E of minus S A star ds, correct? Sorry, here also it would be S. So this was the controllability Gramian matrix. So W of, okay, sure. So where W of this was 0 comma T, okay? So this was the matrix which we called Gramian matrix. So over here we know that this rank is 2, so this Gramian matrix is invertible, and so the control would be given by this, okay? So over here so now you can clearly, we have already checked that this U hat was having the minimal L2 norm. U hat, so maybe let me just U. So U has this U, okay? This U we given by 1, has minimal L2 norm. Okay. So in this particular case you already knew that what will be the optimal control, but what we'll be looking at, so over here what we saw that this functional J was just containing U square, right? So we were just trying to understand how to minimize the cost of the control, but over here the functional might have the states, I mean it could include the states x, y, okay, over here. So you could have x square, y square. So how to deal with that? So that would be the general question, okay, and that we would be addressing, okay? So this was something that you already knew, and now we'll start some new thing, okay? So our goal would be that suppose you have a functional J. So as of now let's not talk about the control system. So assume that you have a functional given to you, and the goal is to find the maximum or minimum value, okay? But in the whole duration what we'll be talking is how to get minimum. So once you can understand that how to obtain the minimum value of some function, you automatically get how to get the maximum value, right? So suppose you have a problem where you want to maximize this J, okay? So what you do, you just define J tilde to be minus of J, correct? And now you try to minimize this J tilde. Then the maximum value of J would be minus of minimum value of J tilde, right? Or if you want to write further, so J tilde is nothing but minus of J, okay? So it's the same, the question is same. So the question is you have to optimize this functional value, so either maximum or minimum, okay? So this is the main goal, that you have to minimize the value of the functional, okay? So let us see how to do that. So we will denote this delta J, okay, that is the change in the value J, okay? So where x, this delta denotes very small change in x, Okay, so this jx plus delta x minus jx, if you do the Taylor series expansion, you will get this kind of a series, okay, where delta j is the includes the first derivative, delta 2j includes the second order derivative of j. Okay, so more precisely, this delta j is given by this, and delta 2j is given by this, and so on. Okay, but for our case, like, this would be these two are sufficient. Okay, you will see how. So it's analog to what we have seen in functions. So when we have multi-valued function or just real valued function with real variable, so there you just have to take the first order derivative, then you find f prime x equal to 0, and then you check whether the sign of double derivative is negative or positive, right? So the same thing applies here. Okay, same thing has been generalized in this setup for a functional instead of function. Okay. So a functional j is said to be have relative optimum. So optimum basically either maximum or minimum at x star if there exist, so this should be epsilon, if there exist epsilon greater than 0, such that for all functions x in the domain d omega. So okay, so here for all functions means for all admissible function, like over what. So when we say that we are trying to find this minimum of this functional, so this xt cannot be a random function, it should be on a sum set, right? Either you can put condition like xt should be continuous, or xt should be differentiable, or x2 should be bounded between 1 and 2, like that kind of constant you have to put. So over what set you are taking the minimum or maximum, right? So you have to understand what will be the set, okay, for this xt. So over here, this is what it means, that for all functions x defined in the domain omega. Okay, so this is called, in this case you are taking all kind of function. Okay. So this is just the general definition. So over here we are considering all functions which is defined in the main set. So here omega is the set where we are concerned. Okay, so when this x minus x star is less than epsilon, that is, so suppose you have this curve, so suppose this is a function xt. So what you are creating basically, you are trying to create a neighborhood around this xt. Okay, so that if any function you choose, that should be in this neighborhood. Okay, so the value of x should be in the neighborhood of this green line. This is what it means, that it is optimum at x star if you take any x which is in the epsilon neighborhood of x star. So this is your x star, green line, such that this increment this delta j should have a fixed sign. Okay, so this delta j, if it is greater than equal to 0, what does that mean? That means that, so let me write the implication. So its implication is j of x plus delta x, okay, is greater than equal to j of x. So it's basically telling you that in any neighborhood of, okay, so let me put x star. So in any neighborhood of x star, the value is greater than j at x star. That means x star is the minimum value. Locally it's minimum, right? So here this relative means local kind of behavior, that relative to other points in the neighborhood, that is the minimum value or maximum. So in this case you will get relative maximum. Okay, now the theorem says that this is analog to what you have seen in functions, in the case of functions. Okay, so for x star to be optimum, the first derivative should be 0. So this delta j, x star delta xt, is nothing but this del j del x times delta xt. Okay, so this is the value of this delta, that is the first derivative should be 0. Okay, and for all admissible delta x means for all kind of perturbation. So admissible here means that it should be in the epsilon neighborhood, that's all. Okay. Now a sufficient condition for the minimum is that this, so this is a necessary condition, right? This is necessary, that if it is achieving minimum at this value, at this function, then this has to, the derivative has to be 0. Okay, and in case for minimum value, so for sufficient condition is that the second derivative is, if it is negative, then you can directly say that this is the minimum value. I mean, minimum value means that you will get x star, okay, such that j of x star will have minimum value. Okay, x star, we are not talking about x star to be minimum or maximum, we are talking whether j x star will be minimum or maximum or not. Okay, okay, so this is the theorem. So we'll see few kind of problem, like what kind of optimal problems are there. Okay, so we'll see mainly two types. So one case is where, so okay, so when we are talking about the control problem, so the first thing is that will be given a system, and there will be initial condition to that. Okay, now the question is when the terminal data is fixed or not. So if terminal data is fixed, this is that kind of problem, that fixed end time and fixed end state. So fixed end time means that time is also fixed, that okay, the capital T will be 5 or 4. Okay, and fixed state means, final state means that the final state what we want. Okay, so what output we want at what time is fixed. So you are demanding that okay, at 5 minutes I should get reach to this data point. Okay, this is the first kind of problem. The second would be that the final time would be missing or final data is missing. I mean, you don't care. So for example, suppose you want to for a practical example, what I can say, suppose you want to study a reaction, okay, or anything, whatever you see. So suppose you want to study a system where time is not important to you. Okay, so you want certain output. That output could take longer time, you don't care. What you care is that the functional what you are trying to minimize should attain the minimum value. Okay, so your main goal is that you want to reach the desired data. Okay, but you don't want to reach very early, or you just want to reduce the cost. So you want to reduce the cost, you want to reach the final data as well, but you don't care. It can, I mean, about the time. So if it takes 5 hours, it's fine to you. Okay, so in that situation you don't care about time. So time could be anything, but the final data is fixed. The other case would be that you fix the time, that okay, I need at this time I need something. Okay, so the time you fix, but you don't care about the terminal data. Okay, third case is that you don't care about both of the things. So neither care about the terminal data, you nor care about this time, that what time you want. Okay, so in that case, with this kind of problem we'll see mainly. So the main goal would be to optimize the functional. Okay, okay, so let's begin with this one. So over
This
here, yeah,
don't care about the final state means what exactly it means.
I mean, you can
Means
think
it can
it
do any.
as just as a mathematical point. I also don't know
Okay.
any application, but as of now, you can just think about it as a mathematical question. That okay, since
Okay.
you understand, right? So you just don't care about
Yeah,
the
yeah, I understand. Yeah, I also couldn't able to find some example practically. That's
So
why.
practically, I am also not able to understand that.
Yeah.
Okay, what
Okay.
because when you are talking about controllability, that means that you want to reach certain data.
Yeah, right.
So over here, you can think of it as main as a optimization problem rather than thinking as a control problem.
Okay, okay.
Yeah, in that sense. Okay, so this type 1. Okay, so here also we'll have two kind of type. So the first is not coming from this control problem. So you just have a functional. Okay, you just have a functional, and you have some data that okay, that at t point. So you can consider like this, that you have two time point. So this is t naught, this is capital T. So what you are doing, you consider all the functions such that at t naught it is this and at capital T it has this value. Okay, so maybe this is my y-axis or x-axis. So you fix that, okay, at t naught it should reach this and at capital T it should reach this point. That's all you care. Okay, so you have to just minimize these functionals over the set of function which starts at this point and ends at this. So maybe you want to study the functions like this, whatever, I mean, whether it's continuous or discontinuous, whatever, like this kind of function. So it should at 0 point t0 point it should take this value and at t it should take this. Okay, so here we are not talking about any control problem, just you have a functional, you have the initial time, final time, everything is fixed. The initial point where at t naught where the function will take the value, this is also fixed, this is also fixed. Okay, so you only have, the goal is only to minimize this functional j. Okay, so over here when you try to calculate, so you try to calculate this kind of analysis, that you calculate del j, you expand it by Taylor series, and then so you will have to use this functional, this form of the functional. So when you use it, what you get is this delta j equal to 0 will give you this condition, and this is called Euler's equation, that del f by del x minus d dt of del f by del x dot. So here x dot is basically the derivative of x. Okay, so this x dot, I mean x dot basically means this kind of thing, d dt of x. Okay, so you want to, I mean this condition is what you get in this particular situation. Okay, now yeah, that's all about the type 1. So here we don't care about, I mean we don't care whether the xt, from where xt is coming, you vary over all xt which is taking, which is of this kind. Okay, in the second one what you have is that you have the same functional, okay, but you have one more restriction. So over here what you had, that okay, at t naught it should take this and at capital T it should take this value. Okay, but over here you have one more condition which is this. Okay, that the x and x prime should satisfy certain relation. Okay, so okay, let me tell you. Okay, as of now you can consider we are talking in R, but this can be extended in Rn. So this x can be in Rn, but as of now you just consider as R. So when you consider just as R, you don't have to worry about the control, right? So see, if you have this kind of system, x prime equal to 5x, okay, so you can say g is 5x minus x prime. So this is the g, that g should be 0, so 5x minus x prime is 0. So now what you are saying, that this functional should have minimum value, okay, where the function x is coming as a solution of some ODE. I mean, I am taking a particular example, right? Because this x prime denotes the differential equation. So what you are demanding is that g of x prime is 0. This is nothing but an ODE, right? So this is nothing but an ODE. Correct? So this is the first order ODE, and what we are saying, that the function x over which we are trying to minimize should come from a solution of an ODE. Okay, and that ODE should satisfy these two conditions. So see here, this capital T is also fixed, this is fixed. Okay, now how to solve this? Let's see. So you define a Lagrangian. So similar kind of thing, right? In the analysis also, like when you study these functions, different this finding maximum minimum value. So when you are given some constraint, that okay, you have to minimize certain function, but given the constraint that it should satisfy some kind of equality or inequality, there also you use Lagrangian multiplier and then you do the analysis, right? Similar analysis can be extended to this functional and it can be done as follows. So define a Lagrangian we will take this function, so this f, okay, plus lambda t times g. Okay, so g is the constraint. Okay, or here what's, so this is the constraint. This is a function of t, so this is unknown to you. Okay, so this is not known, lambda t is not known, so you consider this kind of function L of x t x prime t lambda t to be f plus lambda times g. So when you will go in Rn case, so this is the dot product and the lambda t will belong to R of k where this g is belonging. So if g is belonging to R3, this lambda is also in R3. Okay, and so that this should make sense. I mean, okay, we'll see examples. So as of now, just consider that you define this Lagrangian. Using this Lagrangian, you define an augmented functional. So instead of studying this function, you now study this functional. Okay, so j to be t naught to t L of, so here L and dt. Okay, so now again the constraint is the same, that under this constraint. Okay, so now when you do the similar kind of analysis for this j, what you get is this kind of equation. This is the Euler-Lagrangian equation. So here both the names appear because of this Lagrangian function. Okay, so this is the Euler-Lagrange equation, and this says that the partial derivative of L with respect to x minus time derivative of partial derivative of L with respect to x prime should be 0. Okay. So this is the condition, and this is nothing but what you have been given. So if you see this L, if you differentiate this L with respect to lambda, so you'll get g, right? So this is independent of, okay, I think here there will be no lambda, I have written it wrongly. Correct, because f is independent of lambda. Okay, so this is independent of lambda, this function capital F. So when you differentiate this L with respect to lambda, what you get is g, right? So this del L upon del lambda g equal to 0 is nothing but your ODE. So this just represent the ODE given to you, or the constraint. Okay, so let me write the constraint. Okay. Okay, so as I mentioned that it can be extended to higher dimension where xt belongs to Rn, lambda g belongs to Rm. In this case, this Euler-Lagrange equation can be written in this form, that del L by, so you take the partial derivative with respect to each of the states. So del L by del xi minus ddt of del L by del xi dot equal to 0 for all I in 1 to n. Okay, and this gj should be 0. So gj is nothing but the constraint. So you can have m number of constraint and for each m you need lambdas. Okay, so this is gj of x dot is equal to 0. Okay, so now let us look at few examples. So I am picking the same example what I introduced in the very first slide, this example, but now instead of having this functional, so here the goal was to find the control which has minimum L2 norm. Okay, but now we'll look at a different functional. Okay. So see, this is the extra term what we are adding. So now we don't want just the control to have the minimum value or minimum L2 norm. We want this whole x square y square plus u square, the integral should have the minimum value. So we are considering the states as well in the functional. Okay, where this x, y and u are coming as a solution of this equation, this system. Okay, so here we have some constraint, right? This is the constraint, this is the initial time t naught, this is the final time, this is the initial data, this is the final data, right? So now let us, so what we'll do,
Selecting this functional is arbitrary.
Sorry,
this functional we are selecting x square plus y square
correct,
plus u square.
mm-hmm.
That is there any way to fix that, or it is a
Fix
like
in the
random?
sense?
Now, how
Oh,
we
okay. You are saying
this-
that how to choose my function.
yeah.
It depends on you, like what you want to minimize, right?
Okay.
So in general, when okay, I understood. So I think you are asking about some practical significances, is it?
Yeah. Yeah.
Yeah. So it depends. Like you just want the cost to be of the minimum value. Suppose you are, how should I
Suppose
give?
energy, if I take energy as my cost function, I can.
Correct, correct. So energy is
Okay.
related to the states, right?
Yeah.
So
Okay.
this kind of thing.
Okay.
So over there you will have to include this x square and y square. uh, what example? You can consider the chemical reaction as well. Any example in that case. So you don't want the heat to be too much so that the flask blast.
Okay. Okay.
Okay. So now let us consider this example. So here we'll again try to formulate the system. So let me just quickly write what is the, so let me just quickly go to this equation. So okay, so our goal over here in this problem is to get to this system. Okay, so once we get to this kind of system, we'll try to solve it. That's it. Once you get the solution, you will get the optimal thing, right? Optimum, either it can be maximum or minimum. Okay, so over here we are just talking about the optimizing the function. So let us see. So over here what is given to you. So let me first write what is g. So g is, the first thing is y plus u. So it is of in R2. So you can consider g1, g2, or call it as g, is y plus u, and then you have minus x. Sorry, uh, y plus u minus x prime, and then minus y prime. This would be your g, the constraint, right, or the differential equation. The functional f, okay, is x square plus y square plus u square. Okay. Okay, and then these are the boundary condition. So let me, maybe I should write. So x at 0, y at 0 is 0 0, and x at 5, y at 5 is 1 1. Correct. So let me just copy it. Okay, so this is given to you. Now let us see what was the equation. The equation was del L del xi minus ddt of this. You have to equate it to 0. Correct. So let us first define what is L. So L was what? F plus lambda times the constraint, right? So here it is F plus lambda, okay, dot product with G. So lambda would be lambda 1, lambda 2, dot product with this G1, G2. So this is nothing but x square plus y square plus u square lambda 1 times y plus u minus x prime plus lambda 2 minus x minus y prime. Okay. This is the Lagrange's functional. Now what you have to do, I have to calculate del L. So let me write the Euler-Lagrange equation. So it was del L by del xi. Okay, so over here you see, here my x is 3. I mean, we have 3 states, not states, but the variable involved is 3. So one is x, the other is y, and the third one is the control u. Right? So over here my capital X would be x comma y comma u. Okay. So Euler-Lagrange equation would be del L by del xi minus d dt of del L by del xi dot equal to 0. Right, so this is the Euler-Lagrange equation. So let us try to see what it appears in our case. So let us first differentiate L with the first variable. So with respect to x. Okay. So I am writing del L by del x minus d dt, del L by del x dot, okay, or x prime equal to 0. So if I do, what I get is del L by del x is 2x and then over here you have minus lambda 2. Is there anything? That's it, right? That's, and then you have minus d dt of del L by del x prime. So del L with respect to x prime, it appears here, right? That's the only place where it appears. So you'll get minus lambda 1 equals to 0. So sorry, so what you get is lambda 1 prime t equals so this is plus lambda 1 prime, right? And then you send it to the right hand side. So what you get is lambda 2 minus 2x. So this is lambda 2t minus 2 of xt, right? So this is your first equation. Now the second one would be del L by del u. Okay, so let me do it here somewhere. So you have to do del L by del u minus d dt of del L by, sorry, del y first. Let us first do del y prime equal to 0. So over here del L by del y would be 2y, and then you will have plus lambda 1, and then what else we have? That's it, right? And then minus del L by del y prime, you will get minus lambda 2, right? So from here, so you'll get minus lambda 2 and then differentiate. So minus lambda 2 prime equal to 0. So from here you get lambda 2 prime equals minus 2y minus lambda 1. So this is the second equation what you got. The third one is del L by del u. If you do, you will get 2u and plus lambda 1 and then when you do plus minus d dt of del L by del u prime, right? So del L upon del u prime. So you don't see any term, right? Del u prime, there is no term of u prime. So what you get is just 2u plus lambda 1 equals 0. So you get 2u plus lambda 1 equals 0. So from here you can get the expression of the control, right? So u can be given as minus lambda 1 upon 2, right? Why? Because we have the differential equation for lambda i's. So if we can solve that lambda I, we'll get the control u, right? So this control what we are getting is the optimal one, and corresponding to this u we'll get if you substitute this u in this system, okay, we'll get the optimal x. So when you substitute all this in the functional here, you'll get the minimum value or maximum value, okay. So let me write it completely. So what you need to solve is, so to get optimal solution, we need to solve so let us write the system. So first thing is we will have to write this g, right? Or you can already see del L by del lambda, this condition, okay, or this one, that each component will have to be equated to 0, which is the constraint. That's it, it's given to you already. So over here we have x prime equals to y plus u, right? So x prime equals y plus u, and then you have y prime equals minus x. This is the first equation. So over here you can replace u by minus lambda 1 by 2. So replace it by, sorry, minus lambda 1 by 2. And the other equations are lambda 1 prime equals lambda 2 minus 2x and lambda 2 prime is minus 2y minus lambda 1. So you have a system of 4 first order differential equation, right? And the boundary conditions are so this is equation and this is the boundary condition. So about x and y it was given to you. So x0 y0 is 0, x5 y5 is 1. So x0 equals y0 equals 0 and x5 right, this is what you have. This is the boundary condition that you have. So over here you might be looking, if you think that we have 4 equations and you have 4 boundary conditions, but it seems that okay, we don't have boundary condition for lambdas, right? Or you should have, suppose instead of these two, so instead of these two you might be expecting that what is lambda 1 0 and lambda 2 0. If you get this, then you can directly solve that. E of ta times the initial data, which is x0 y0 lambda 1 0 lambda 2 0. This is the solution of this equation, but this is not known to you. But instead of this, you know these two conditions. Okay, so you can utilize these two conditions to get this value. Okay, so I'll not solve this. Okay, but you can solve. Okay, I'll solve one problem at last, which is very simple. Okay, so this I'll not solve. So you can clearly write this as a matrix form. So I could give you, so you can either go by two ways. Okay, so matrix way would be too long, that you'll have to write the 4 cross 4 matrix, then you will have to calculate the exponential and all. If you really want to know the solution, I would suggest you to first solve the uncoupled one, that is, you solve this one. So you'll get the value of y, right, and then you substitute it here, and I don't know how complicated or how easy it would be, but you can use this kind of thing, that solve the uncoupled one first and then try to substitute in some equation where you can get the solution easily, or where there is no other. So suppose this lambda 1 was missing, then you can clearly solve this, substitute it in this equation, you will get x prime, right? Okay, here also there is a coupling, so you cannot do that also. Okay, so I think this would be a bit, calculative, that if you want to go through the calculating the matrix and exponential of it, that would be lengthy, but that would be straightforward, I would say. I don't know. Okay, so you just try if you want, that how the solution looks, but you can understand that okay, the solution will exist for this system. We have 4 equation, we have 4 boundary condition, so it will have solution. Okay. Okay, now let's come to this problem. So over here you have this system, okay, and you have to minimize this functional, 2x square plus 3u square. Okay, so let us again do the same thing. Okay, so let me first write here itself. So what is my, so g1, or over here we just have one equation, so g of, is there any question? Okay, so g of x comma u would be, sorry, x prime u prime u prime is 3x plus 5u minus u prime. Okay, so this is my g. Capital F is given by 2x square plus 3u square, and Lagrangian, if you want to calculate, it is just the f, which is 2x square plus 3u square, and then you do lambda times g. So over here we just have one component of g, so it's just the usual multiplication. So lambda times 3x plus 5u minus u prime. Okay, so let me just okay, so now let us try to solve the Euler-Lagrange equation, or try to get what the Euler-Lagrange equation is. So del L by, first we'll do with del x minus d dt of del L by del x dot or x prime equals 0. So over here this is nothing but del L by del x. If you do, you'll get 4x plus 3 lambda and then minus del L by del x dot. If you do, oh, I think so, this is x prime, right? So this is x prime. So del L by del x prime, if you do, you'll get minus lambda, so you'll get plus lambda prime equals 0. So this is one equation what you get. The second one we can try use similarly, del L by del u minus d dt of del L by del u prime, sorry, correct, equal to 0. But here del L by del u prime is 0 and del L by del u is nothing but 6u and then plus 5 lambda equals 0. So from here you get the value of lambda, sorry, u in terms of lambda. So u you can write minus 5 upon 6 times lambda. So this you can consider the second equation. Okay, now you got the, so this is the Euler-Lagrange equation what we have obtained. So now to get the optimal solution, we have to solve the following. So the first one is that, so here also it is x prime. So first thing is that we'll want g to be 0, g, so which is x prime should be equal to 3x plus 5 times u, and this lambda prime, so u you can replace by minus 5 by 6 lambda, so you'll get minus 25 by 6 lambda this one, and lambda prime equals minus 4x minus 3 lambda. Okay, and the data what you have is, so x0 is 1 and x1 is 2. So again similar kind of thing, you have two equations and you have two conditions to solve, right? So using these two conditions you can get the solution for this equation. Okay. So okay, I should mention once at least. So see, from when you solve this, what you get is, maybe right, so when you solve, after solving you get xt and lambda t, right? Okay. From, so this you can consider the optimal one, so in the sense that, okay, sure, okay, xt and yt, now you can substitute this, you can use the value of lambda to put here in 2, so you get u of t. Okay, now these, now from here, so the xt and ut so let me denote it by some symbol, x star or So this is the, let's say, optimal one. Okay, so you got x hat lambda hat, and using this you can get u hat. Now when you substitute in this j, so j of over here we had x square and u square, so j of x hat and u hat will have the minimum value. Okay, so once you get the solution, you will get the minimum value of j, and you can get what the minimal control is and what will be the state. Okay. Okay, so now so okay, that's it. So let us come to this problem. So you see everywhere, although I'm not checking that controllability, but here you can see you just have one state and one control, then obviously it is controllable, right? Okay, so we don't have to check that controllability. So the controllability is there. So from here you know that x comma u exist, you know that such pair exist, right? There will exist u, so that the solution x at 0 will be 1 and x at 1 will be 2. The question was to find the control so that this is the minimum value. I mean, this functional has minimum value or optimal value as of now. Okay, so using this you got this x hat u hat. Now you have to check the double derivative, which is I noted by delta 2z. If this is negative, then you can say that this is the minimum value. So I should not write minimum value, have the optimum value. Okay, so this u hat is a special. This u hat is not just a control, but it is the control which gives the minimum value of j. Okay. Okay, now let's come back to this question. So over here, this capital F is given by x square plus 2x plus u square plus 1. G is given by 5x plus 3u plus 7. Okay, so the Lagrangian would be just x square plus 2x plus u square plus 1 plus lambda times this g, which is 5x. Sorry, g would be minus x prime as well. This is plus lambda times 5x plus 3u plus 7. Okay, let me just okay, so this is the Lagrangian. Now again the same process will repeat. So would you like to do? Maybe you can try. So I'll write the formula. You just compute. So this you have to compute del L by del x minus d dt of del L by del x dot or del x prime equals 0, del L by del u d dt del L by del u prime equals to 0. Tell me what you get from here. This is the Euler-Lagrange equation. So here we'll get x prime equal to 5x plus 3 plus 7. Boundary conditions. What did you get here? It's easy, no?
Yes.
So here you got
First equation will be 2x
okay,
plus 5 lambda
okay,
minus 5, 5 lambda dot. No, sorry, minus lambda dot equal to 0.
I think you missed something, right? The first thing is that here you missed this point.
Yeah, 2.
So 2x plus 2, and it would be not minus, plus, right? So you have minus of ddt of this. So this is minus lambda x dot.
Okay.
So minus of
Plus
minus lambda prime. So it would be plus, right?
Yeah.
So it's plus here.
Plus
And
2 also.
yeah,
Equal to 2.
correct. Plus 2 equal to 0. And when you differentiate this second one, you get
u 2u plus 3 lambda.
plus or minus?
Sorry, minus 3.
Minus 3 equal to 0. So I hope in the earlier one, what did I do? I sometimes I feel I added plus. Oh, here also I think I did plus. It should be minus, no?
Yeah, first equation is correct.
Here also minus. I think I did this mistake everywhere. I feel so. To you, so which is del L. So del L by del L by del U. If I do, I'll get minus lambda 1. So here it's fine. No. Here I'll get minus lambda 1. Let's see, here is a minus sign. Okay, so I think I did wrong calculation. Okay. Okay. So now let's return back to the problem. So you got this kind of system. Now from here you can again get this lambda, which is 2 by 3u. So you can substitute it here, right? Sorry, I mean u is equal to 3 by 2 lambda. So when you substitute, you will get 9 by 2 lambda. And the equation is lambda is given by 1. So lambda prime equals minus 5 lambda minus 2x minus 2. Okay, so you got again the similar kind of system and with the some boundary condition. So over here this x1 x2 is some prescribed value. Okay, so this is not to the next case where the terminal data is free. So over here x1 x2 means that it is fixed, some x1 x2. Okay, so now we'll come to this terminal cost problem. Okay, so where terminal either time is not fixed or terminal data is not fixed or both are not fixed. Okay, and the goal is to minimize this functional. Okay, so over here you can have this additional term which is the value at capital time t. Okay, so this is some function which is of time capital time t and the value of x at capital time t, although this t may or may not be known to you. Okay. Okay, so when you try to do the similar kind of analysis, so over here what you do, one new step is this one, that you define this kind of functional. So instead of looking this functional, you look at this functional. So f plus, so there is one additional term, ds by dt. Okay, so what this ds by dt, if you integrate, what did you get? So if you integrate this one, you will get s at t and xt minus s at t0, x at t0. Okay. This is the integration of this part. Okay, so now this st is the what you have seen in the previous functional, and this is something which is extra, correct? but this is the quantity which you already know. So this s function is given to you, so you know how s is acting. Okay, so s of x comma t is known to you. This x at t naught and t naught is known to you. So when you have this system ODE, the control system, you know the terminal point and terminal data, initial point and initial data. Okay, so over here the terminal data or terminal time is what we don't know, but this is always known. So this is something, so this whole quantity is something which you know, so this is known to you. Okay, so the goal is just to minimize this unknown part, right? This is something which is fixed, correct? So if you can get x hat u hat, okay, which minimizes this functional, okay, so when you get the value, so when you get j of x hat u hat, when you calculate, you'll get some value, right? Now what you have to do, you have to just subtract this one. So suppose, and now you what to do to get the minimum value of j1. So j1 at u hat and x hat, okay, whatever, would be nothing but j j at x hat u hat, and you just subtract or add whatever. So here you will have to plus s of t naught x at t naught. So if you do this, you will get the minimum value of j1, but it will be attained at the same point u hat x hat where the minimum of this functional is attained. So instead of studying this functional, I mean optimizing this functional, you have to optimize this functional, this new functional. Okay. Okay, so here it's nothing but, so you are just writing this s in a derivative form, that's it. Okay, so now you do the similar analysis, that you take the Taylor series expansion, you take that first derivative to 0, all those things. So what you will get is this kind of equation. So okay, the Lagrangian, okay, I have not mentioned it here. Okay, here I have mentioned. So Lagrangian is this function f, okay, just like before, and this one just like before, right? So this is nothing but g, right? F minus x prime. So here, yeah, it's written here. So x prime is this f. So g is f minus x prime, which is written here. So this is something which is new. If you consider from the, if you compare from the previous case, this is something which is new here, and this is because of this addition of this new functional. Okay, so this new functional is counted here at this point. So this is due to that term. Okay, so it's similar to what we have seen in the last case, and here the equation is given in this form. So del L by, it's the same. Okay, what we have seen. What is extra is this one. Okay, and this. Okay, have I included that one? Okay, so these two are actually the same. So let me circle this. Okay, so here it's nothing but, you know that d dt of del L by del u prime is 0. So that's why it's written separately, right? So whatever examples we have considered in the last, because when we consider this ODE, right, when we consider this kind of ODE, it don't have u prime anywhere, right? The control is just u, not u prime. So that's why every time in this L, u prime is not going to appear. Okay, so this del L by del u prime is always going to be 0. So that's why it's just del L by del u equal to 0. I mean this equation. These two are the similar to the last case. This is something which is new. Okay, and this is where, so if you look at this term, you see this delta t and this del x dot t. Okay, this represents that, okay, if time is not fixed, then this delta t represent the perturbation or the small change in the capital time t. Okay, so in case, so I have said that there will be 3 cases. In one case, when time is fixed, so when time is fixed, okay, this delta t will be 0. Okay, so this is some way it's representing It is appearing in the system in this equation because of this, whether t is varying or not. And this condition is appearing whether the terminal data is varying or not, or is it fixed or not. So this is corresponding to the terminal data, whether it is fixed or not, and this is corresponding to the final time, whether it is fixed or not. Okay. Okay, so it will be more clear when we'll go to example probably. Okay. Okay, so in this case, actually, if you look at this L thing, this equation of L and the involvement this L involves is too much. Okay, so when you will try to compute this and try to solve it, it would be a bit tough to solve. Okay, so for that, what we do, we define Hamiltonian function, okay, which is of this kind. So it is more similar to what we have seen earlier. So where we define Lagrangian as f plus lambda times something, g, the constant. Okay, I think here I have done a mistake. This Hamiltonian, just a second. This thing should not be there, I guess. This x prime should not be there. I mean, this is the different thing. Okay, I don't know. Yeah, this should not be there. I think I've done mistake. So this, I think, okay, although I will check, but I don't think this is there. This should not be there, I guess. Okay. Okay, so this function is somewhat similar to the Lagrangian what we have considered earlier. I mean, this, although the constraint is not there, we just have the x prime. So whatever x prime is equal to it, so we just have that term. Okay, so lambda times that. So this is called Hamiltonian. Okay, and if you try to, I mean, convert these equations, these Euler-Lagrangian equation, in terms of h, this is what you get. Okay, so del h upon del u is 0. This del h by del x is minus lambda prime. So this will give you equation of lambda, a differential equation of lambda. Okay, this, okay, you see this del h by del lambda, if you do, you'll get f, right? So this is equal to f, and this is x dot of, so this is the given differential equation. Okay, or what, here we used to write it as del L by del lambda. Okay, in this case it's not there. Yeah, here also it should be. So del L by del lambda, when we do it is 0. So this is nothing but g equal to 0 in this case. So here this represents the equation, differential equation, which is given to us, right? Here that condition translates in this form. Okay, so that's why here there will be no x prime here. Okay. Okay, so this star is just representing the optimal thing. Okay, so you don't have to worry about this star. Okay, you can forget also this star maybe. Okay, when you solve this, you will get the optimal one. Okay. Okay, so this is the given differential equation. This is given differential equation of lambda. Sorry, this is the differential equation of lambda that you will obtain, and this will give you the value of lambda in terms of u, right? So if you see in the last examples, what we were doing, one equation was giving, one of them was giving us differential equation of lambda, the other one was giving the value of u in terms of lambda. So this will give you lambda or value of u in terms of lambda. Okay, and this is again the corresponding to the terminal data, what we are saying. So when terminal data is fixed, this del t will be 0. When the terminal data is fixed, this del of xt will be 0. Okay, so this is, so from now onwards, when we'll talk about this terminal cost problem, okay, instead of looking at Lagrangian equation or Euler-Lagrange equation, we'll look at this equation, okay, coming from the Hamiltonians. Okay, so from now onwards we'll try to solve this system. Okay. So let us start with this problem. So x prime is given to you, so let us write quickly. So see here, what we need is basically this small f, capital F, and this h. Okay, in all these three terms, you see we are differentiating just h. Okay, so let us see quickly. So f is given as 5x plus 9u, and so here s is also involved. So s, okay, so I'll explain first. So you see in the expression what we have introduced, the general functional. So where there we have put s xt comma t. So this is nothing but, over here this is 2x square t, or if you want you can write it as 2xt square. Okay, but you consider this as two variables, so you consider this as some x and this is time t. Okay, so this function I can say this sx comma t is 2 of x square. Okay, so that's all I'll write. So s is 2 of x square, and what else I need? This capital F is given as 3 of 3x square plus 8u square. Okay, so that's all I need. Okay, so this is what's given to you. Now you can define Hamiltonian h from these things. So what the f plus lambda times this small f. Okay, so this is nothing but h can be given as 3x square, 3x square plus 8u square plus lambda times 5x plus 9u, right? This is the Hamiltonian. Now we have to solve these equations. So we'll have to determine what the equations are. So the first one is del h by del u equal to 0. So del h upon del u equal to 0. So if I do, what I get is 16u plus 9 lambda should be equal to 0. So from here, just as I mentioned, that will get u in terms of lambda. So from here you get u equal minus 9 by 16 lambda. Okay, so this is 1. Second one is that lambda prime should be minus of del h del x. So lambda prime is minus of hx, right? So this is lambda prime equals, so minus hx would be minus 6x minus 5 lambda, right? The third, so this is the second equation. If we look at the third one, it's just the given equation. X prime is h lambda, which is f. So it's like, so this x prime equals 5x plus 9u, the given equation, right? So this is the third one. Now the fourth one is this one. So over here in this particular problem, you see t is free, but xt is fixed. And fixed, I mean, in that sense that if you fixed, I mean, it's given in terms of t square, but that doesn't mean that this is free. Once this t is fixed, this is also fixed. Okay, so the only variable is capital T. Capital T is something which is changing. This xt cannot take arbitrary value. It is given as a function of capital T. So this is fixed in that sense, but this is free. T is free over here. Okay, so this would mean that this delta t, the change in time, that you don't have to this is non-zero. I'm saying here, I'm saying that delta of xt should be equal to 0. So if I put it here in this equation, what I get is h plus st times delta t equal to 0, right? Because delta x is 0, delta xt. So for the fourth equation gives this me. So this is okay. So this is actually evaluated at capital time t. Okay. So this gives you that h at capital time t. Now what is st? So over here you see s is just a function of x. So its derivative is 0. So this is 0. So h of capital T. Okay, so one more thing. So this is true for all delta t small enough. Okay, so all admissible delta t you can say. So this is for all delta t. So this would imply that h at capital time t plus st at capital time t, which is 0, is equal to 0. So this is the fourth equation. Okay, so again you got a system of equation of x prime and lambda prime, of lambda x and lambda. Okay, so with this, so what are the boundary condition and all? So let me write it here. So you have this equation. So x prime equals 5x plus 9u, lambda prime. Okay, u you can replace. So here by 9 minus 9 upon 16 lambda. Okay, so it's minus 81 by 16 lambda, and lambda prime is minus 5 lambda minus 6x. Okay, x at 0 is given to be 3, x at capital time t is given to be 2t square, and h of t is equal to 0. Okay, so you see over here this t is not known to you, and for that you have been given this equation. Okay, so this system will have a solution. Okay, so this is the final system that you have to solve. Okay, now let's come to this problem. Okay, so over here this is the control system, this is the initial data, and this is the functional j. Over here this t is fixed. Okay, unlike the previous one where t was varying, but over here this x1t and x2t are varying. Okay, so let us quickly look at this. Okay, so what is f? If you write it in expand, if you expand, okay, so here this is missing. So this is x1 x2. Okay, so if you expand it, what you get is x1 prime equals u, and x2 prime is equal to x2, right? So f will be, it will have two components. Okay, the first one is u, the second one is x2, and this capital F is, so s is what? S of x1 x2 oh. T is 1 by 2 x2 square. Okay, and capital F is half u square. Correct? So we have this. Now from here we can compute the Hamiltonian. So h would be just f plus lambda times, so here this f is 2 vectors, so I'll have lambda 1 lambda 2 times this f, which is u x2. So this is nothing but half u square plus lambda 1 u plus lambda 2. I think I did so wrong. So this is x1, sorry, this is x1, right? So here it would be x1 lambda 2 x1. Okay, so this is my Hamiltonian. Now again I'll have to see all those four conditions. So the first one was del h by del u equal to 0. So if I differentiate it, I'll get lambda 1, correct, So here I am getting u, so u plus lambda 1 equals 0. From here I get lambda 1 equals to minus u. Okay, the second one was lambda prime is equal to minus del h by del x. So here lambda, so here we have two components, right? So the first is lambda 1 prime is equal to minus del h by del x1, minus del h, or simply minus h x1. So h x1 is lambda 2. Lambda 2 prime, if you go, it is minus h x2, which is 0. Okay, so this is and the third one was the just the equation which is given to you, right? So what is that? This x prime equals to u, x prime equal to u, x1 prime, and x2 prime equals x1. Okay, again you can see this is a controllable system. Okay, although here we don't need that also, okay, because here we don't care about the terminal data, right? Okay, so we got this system. The last equation was with respect to this change, so whether t is fixed or xt is fixed. So over here you see this t is fixed, so delta t is going to be 0, but delta xt is not fixed. So okay, one more thing, so let me come to this formula here. So here delta t is 0, so we don't care about this, but what will come here is sx minus lambda at capital time t with del xt. So let me first, so in our case we have two components, right? So let me first write it here somewhere. So maybe I should here. So let me explain it first. So over here we have two components. Okay, so del xt is also like it is del x1t and del x2t. I mean the change in the terminal data, two of them. So we have two components. So here everything means to, I mean, so here this equation reduces to the following. So this is for arbitrary. Okay, so we can directly say sx minus lambda is 0, and that means that sx1 minus lambda 1 is 0, sx2 minus lambda 2 is 0. That's it. So maybe I should write in the next page. Okay, so this is what you get. So this is what you get. Okay, I mean not this one, this is what you get. Okay, so in this case what it turns out to be, so s of x1, if you see, where is s is this one. So you can clearly see sx1 is 0 and sx2 is x2. So sx1 is 0, so lambda 1 is going to be 0, and sx2 is x2 minus lambda 2 equals to 0. Okay, so this is the okay, so this is at capital time t. Okay, it's the boundary values, so I should write it here. So what you get is lambda 1 at capital time t is 0, and lambda 2 at capital time t is nothing but x2 at capital time t. Okay, and t is fixed here. Okay, so let me just write, so t is 5, so this is lambda 1 at 5, and this is lambda 2 at 5, x2 at 5. Okay, so now let me write the whole system that we need to solve combiningly. So system to be solved. So x1 prime is equal to u, x2 prime is equal to lambda x1, lambda 1 prime equals this lambda 2, lambda 2 prime equals to 0. Okay, and what are the, that's it. Okay, u is minus lambda 1, so I can replace here by minus lambda 1, and x1 at 0 is 0 and x2 at 0 is 1. So x1 at 0 is 0, x2 at 0 is 1, and we have few more conditions that lambda 1 at 5 is 0 and lambda 2 at 5 is equal to x2 at 5. Okay, now this is quite simple. Okay, so let us try to solve this one. Maybe I should solve here itself. Okay, so if you see, where should we start with? So you can see this lambda 2 prime is 0, so that means lambda 2 is a constant function. So lambda 2 is constant, and you know that lambda 2 at t is constant value, which is equal to lambda 2 at 5. So it is a constant, so at what the value it takes at 5, it is the same as this one, right? Okay, now the second one what we can choose is to solve. So okay, so I can write here maybe lambda 2 is equal to x2, so let's write that only. So lambda 2 at 5 is equal to x2 at, so lambda 2 at t is equal to x2 at 5. So this is one equation. Okay, now so this lambda is somehow it's known to you, right? It's constant. Now what I'll do, okay, it's lambda 2, sorry. So now I'll substitute it in lambda 1. Okay, so lambda 1 prime is equal to lambda 2, and lambda 2 is x2 at 5, which is a constant, it's not a function of time. So from here I can say lambda 1, this lambda 1 at t is nothing but lambda 1 at 0 plus t times x2 at 5, right? This is the solution of this lambda 1 equation. Okay, now the third equation, let us try to solve this x1 prime. So you know x1 prime is okay, so lambda 1 at 0 is also known, I guess. No, it's not known. Okay, so this is not known, so no worry. So anyway, this right hand side is a function of time. So now to get x1, I will have to integrate this minus lambda 1. So x1 prime is minus lambda 1, which is minus lambda 1 0 plus t times x2 at 5. So here I can integrate to get x1 at t is equal to again x1 at 0. Okay, so x1 at 0 is 0, so I am removing this, and then minus t times lambda 1 0 plus t square by 2 times x2 5. Okay, so this is second, this is third. Now let us go in the equation of x2. So x2 prime is x1, right? And x1 we know this. So what, to get x2 we will have to integrate it again. So let's directly write what is x2. So x2 of t is nothing but x2 at 0, which is 1, plus integration of this x1, so which is minus, so this is minus, minus t square by 2 lambda 1 0 plus t cube by 6 x2 at 5. Okay, so this is the fourth equation. Okay, now what is unknown to us? Look at that. So we don't know the actual value of x2 5, correct? And we don't know the actual value of lambda 1 0. And see if we can somehow figure it out, what is lambda 1 0 and x2 5, we are done. Correct? What we have not utilized so far, let's see. So we have not utilized this one, that lambda 1 at 5 is equal to 0. We have utilized this condition. Okay, so let us see if I so for that let us consider the second equation. So from 2, if I put t equals to 5, so I'll get lambda 1 5, which is 0 is equal to lambda 1 0 plus t is equal to 5 and x2 at 5, right? So we got that x2 at 5 is equal to minus 1 by 5 lambda 1 0. right? So we have got uh, okay, so x2 at 5 is given by this. Let us call this as the fifth equation. Now what else can be done is okay, what else can be done? Okay, here also. Okay, so let us replace x to 5. Just a second. So x to 5, if I lambda 1 0, so I've used this one, so use this one. X to 5 is this one. Okay, I think if I can use this x2 equation, so x2 equation if I use, okay, correct. So see, yeah, so let me go to the next slide. So let me just copy this part. This is the first copy. This is one, then let us copy this as well. Okay, so what you do now, this you already know. Now you can substitute what is lambda 1 here, right? So you'll get x2 at t is equal to 1 minus t square by 2 times lambda 1 0 is minus 5 times x to 5. So plus 5 t square by 2 times x to 5 plus t cube upon 6 times x to 5, right? So I have substituted so using, this is obtained using 4 and 5, right? Sorry, I have used it here using 4 or 5, right? So we got this one. Now it's clearly just a system. So what you do 1, okay, so you substitute t equal to 5. If you put, you get x2 at 5 equals 1 plus 125, correct, by 2 x2 at 5 plus 125 upon 6 times x to 5, right? You can solve 1 minus 125 upon 2 minus 125 upon 6 into x to 5. This is equal to 1, right? So you can clearly, from here you get the value of x2 at 5, right? You got the value of x to 5 now, and so lambda, what was lambda 1 0 is minus 5 times x to 5. So you got this as well. Now you just substitute it here, the ones underlined with black color. So you got the x hat, okay, that is the minimum, I mean where the function will achieve the minimum value. So in this case it's quite, you see there is no coupling. I mean that's why I solved it, because it's simpler to solve. There is no coupling. I mean there is a coupling, but it's in the cascade sense. I mean x1 prime does not involve x1, it just involves lambda 1. x2 prime does not involve x2, it just involves x1, like that. So it was easier to solve, so that's why I showed you here. Okay, now let us look at this problem. So over here, this function f is equal to 4x plus u. This s of xt is given by 3x square. F is given by 3x square plus 2u square. So now you can define this Hamiltonian as f, which is 3x square plus 2u square plus lambda times f. F is 4x plus u. Right? So this is the Hamiltonian. Now the first thing was del h by del u is equal to 0. So you'll get 4u and then plus lambda equal to 0. So from here you get lambda equals sorry, u equals minus 1 by 4 lambda, minus lambda by 4. The second one was that lambda prime is equal to minus del h by del x, right? So minus lambda prime is equal to, you differentiate with respect to x, so you'll get, sorry, so it's lambda prime equal to minus of this h. If you differentiate, you'll get 6x, and here you get 4 lambda. Okay, the third one was just the equation, so which is x prime is equal to f, which is 4x plus u. Okay, and u you can replace from here, which is minus lambda by 4. Okay, now what is the last? Over here you see this t and xt both are free. Okay, so in this case both are, we have to consider both the terms. So if you see what the expression was, so this is the expression, so I'll just write it. So h plus st at t should be 0, because this is arbitrary and this is arbitrary. So the second one is sx minus lambda at t, this should be 0. Okay, so this is because since both are varying, so we have this equation. So maybe I should copy. This was 1, 2, 3, this is third one, fourth one. St at capital T should be 0. So this implies st, if you see, it is 0, right? So this simply means h at capital T should be equal to 0, right? So this is the fourth equation. Oh shit, I erased it. Okay, so this is the fourth equation, and the next one is sx. So sx is 6x, 6x minus lambda, so 6x minus lambda at capital time T should be equal to 0, right? So this, the fifth one is, let me just shift it a bit. So this would give 6x at capital time T minus lambda at capital M T is equal to 0. Okay, so you got from here that lambda T is equal to 6x at capital T. Okay, so again you see, so you have this system, right? So it's like x prime equal 4x minus lambda upon 4, and lambda prime is equal to minus 4 lambda minus 6x, x at 0 is given to be 10. Okay, and h at capital M T is equal to 0, and then lambda at capital M T is equal to 6x at capital M T. Okay, so in this case you will get optimal time as well, that T star. So okay, so if you solve this system, right, so this is no problem. So for x prime you have this equation, no issue, but for lambda prime you have to look at these two conditions, right? So if you solve this whole system, you will get a T. So from here what will you get is T hat. Okay, when you solve it, you get, so you'll get x hat, u hat, and t hat. Okay, and when you substitute this, so you will solve okay, so when you get the solution of x hat, u hat, t hat, you can solve the system to get x at t hat is, sorry, I should write in this way, x hat at t hat will be the xt hat, I mean the optimal terminal data as well. So the output what we'll get is also, I mean it's not optimal in that sense, but if you substitute these things in the functional j, right, that will give you, so you see here you have to evaluate x square at capital time t, so which is this quantity x hat at t hat. Okay, so when you substitute all these things over here, you will get the minimum value of the functional. Okay, is this clear?
And this h evaluated at t means we will get 3x square of t plus
Correct,
2
2u square of t plus lambda at capital T plus 4x at t, and u anyway you know u is given as minus lambda by 4. Is there some issue?
No, I just asked.
Okay, yeah. So anyway the point is you will get solution, I mean using these two equation, and I mean when you will try to solve it you will ultimately land up to this t hat, so you will get some particular value of t, and this x hat, lambda, u hat, everything, lambda hat. So I should say not u hat but lambda hat, okay, because this system does not involve u at all. So you'll get lambda hat, but then if you substitute it you will get u hat, because you know u is given as minus lambda by 4, and then you can use it to get x hat at t hat. Okay, okay, so that's all I had to say for today. Okay, so do you have any doubts or question?
And this Lagrangian and Hamiltonian, what is the difference?
So see, both are like giving you the conditions from where you can get the optimal thing, right? The point is when you try to solve this Lagrangian equation, you can try for this equation, maybe you can try for this system. Okay, you will see that there will be a lot of things that will be coming. So this Hamiltonian actually reduces your computation. When you use the Lagrangian way, you will get a lot of things which would not be that easy to handle. This Hamiltonian reduces the this complexity. Okay, if there is no other doubt, we can stop here. See you next week then.
Okay.
Bye.